So now moving on to the next problem, that is design graph with shortest path calculator. This is a hard level problem on LeetCode 2642. So there's a directed weighted graph with that consists of n nodes numbered from 0 to n minus 1. The edges of the graph are initially represented by the given array edges, where edges of I is equal to from I to I and h cost of I, meaning that there's an edge from I to 2I with the cost h cost of I. Now we need to implement the graph class, that is graph int takes the parameters int n and int of basically a 2D vector of edges, initializes the 2D array of edges, initialize the object with n nodes and the given edges. So it initializes this graph with n nodes and given edges. Then add is the function in which we taking the edge. It adds an edge to the list of edges where edge is equal to from, comma, to, comma, h cost. It's guaranteed that there is no edge between the two nodes before adding this one. Also, shortest path in node 1 and node 2 returns the minimum cost of path from node 1 to node 2. If no such path exists, we return -1, and the cost of path is the sum of the costs on the edges in the path, right? So this is an example here. So graph basically would output null because graph basically initializes the adjacency list. Then we take the shortest path, right? So this is our first thing. Wait, let me just show you. So shortest path would basically calculate the shortest path between the nodes that are being taken into consideration, right? So just a second. Graph takes n and the edges. So basically this is n, that is the 4 is the number of nodes, and the edges are denoted by this. So let me show you. 0 2 is the directed edge, 0 to 2, or let me, in order to show you in this graph, 0 to 2, so u to v, and the edge weight is 5. Then 0 1, so 0 to 1 we have another node, another edge, and the weight is 2. Then 1 to 2 and the edge weight is 1. Then 3 to 0, so 3 to 0, another directed edge with the edge weight being 3. So you can see this is the graph that we form using the function that is graph, right? So this is the same graph here. Then we have shortest path, so we need to calculate the shortest path. So basically this is the shortest path between node 1 and node 2, that is 3 and 2. So between 3 and 2, what is the shortest path? So you can see, you can sense that we are going to be using the Dijkstra algorithm, right? Since we are required to calculate the shortest path between two nodes. So this is a standard problem. So let me just show you between 3 and 2, what would be the shortest path? That would be, firstly we check 3 to 5. So one path says it is 8, right? If we initialize from node 1, we are initializing the distance to node, from node 3 we are initializing the distance to node 3 itself to be 0, because this is a starting or the source node. Then to 3, since this is only one path, the minimum distance to reach it is 3. Then going to 2, that is our node 2, we add up these edges, that makes it 8. Now we have another path, so we traverse that path. So going over to 1, this basically gives us 3 plus 2, that is 5. So that is the shortest path between 3 and 1. But our aim is to get to 2. So we take this edge, that is of cost 1. So basically 5 plus 1 would give us 6. That is smaller than 8. So that is the minimum or the shortest path between node 1, that is 3, and node 2, that is 2. So 6, that is why we return 6. So this one is covered. Now 0 to 3, we need to calculate the cost between the shortest path between them. So you see 0 to 3, there is no edge. That is why we return -1. So because we're playing with directed edges, right? That is, if the condition was 3 to 0, that is from u to v, then it would have made sense. That is, the shortest path would have been 3. But we cannot, there's no edge from 0 to 3, right? So since this is a directed graph, we return -1. Similarly, 1, 3, 4, we have to add an edge, right? So 1 and 3, 1 is basically the starting node. So 1, from 1 to 3, we add a node of edge weight, an edge of edge weight 4. So that you can see here we have added. So once we added the edge, then we call the shortest path between 0 and 3. Now you can see that between 0 and 3 we can have a path. So from 0 we have 0 as the shortest distance between 0 and 0, since we are initializing the Dijkstra. Then 2, okay, so this, the minimum distance to reach 1 from 0 is 2, and from here to here 1 to 3 we have 2 plus 4, that is 6. So that is the minimum cost to reach here. So that you can see 6 has been updated. So that's how you have to solve this problem. Now that is the explanation. This is the same thing that I did. So now let us get to our in-depth solution, right? So imagine you have been tasked with navigating a complex web of interconnected locations, each with its unique path and cost associated with traveling from one place to another. This is precisely the challenge presented in this problem. So you're given a directed weighted graph represented by an array of edges. Each edge signifies a one-way connection between two locations, complete with a cost. Your mission is to create a graph class that can efficiently manage this network and provide two essential services, right? That is setting up the map, graph int n comma int basically a 2D array of edges. Just like preparing a map for a journey, you initialize a graph with n locations and the given edges. This step lays out the foundation of your navigation. Then we need to plot our new routes, that is by adding an edge, right? So as the journey unfolds, we come across new routes. The add edge method allows us to add these paths to the map, and finding the optimal path, that is the shortest path between node 1 and node 2. Right, so that is the shortest and the most cost effective path, that is the minimum cost from one location to another. So this calculates the minimum cost required to travel from node 1 to node 2. If a path does not exist, it signals your GPS to return -1. So we are correlating it with a real life example. So solving this problem involves creating a powerful navigation tool, the graph class, that not only builds and updates the map as new routes are discovered, but also efficiently guides you to your destination, ensuring that you reach your target with the least possible cost. So our approach one would be the Dijkstra's algorithm, right? So our intuition is that if let us go to this. So algorithm maintains a priority queue of nodes to explore, prioritizing those with the lowest tentative distances. We begin by setting the cost of the source node to 0, as I did, and enqueue it into a priority queue. So we make a priority queue and we enqueue it, that is a minimum heap. Simultaneously, we initialize an array to store the cost associated with each node when starting from the source node. So while there are nodes remaining in the queue, we dequeue the node with the lowest cost, examine whether it corresponds to the destination node, and return its cost if it does. If not, we explore its neighboring nodes, compute the new costs for the neighboring nodes, and if these new costs are lower than the previously recorded costs in the node cost array, we enqueue the neighbor nodes into the priority queue. If the event that destination node cannot be reached, in that event, we return -1 to indicate the absence of a viable path to that destination node. Right? And we implement this approach by creating a graph class with methods of initialization, finding the shortest path using Dijkstra's. Right? So this is basically our diagram. You can see this is how we perform Dijkstra's algorithm. That is, we create a table that has first column as node and the second as cost, and we initialize our source node, that is a start node, with the cost 0. So we set cost is equal to 0, and all the other nodes are initialized with infinity since we are starting the algorithm. And we have a priority queue in which we have stored 0, a, that is the distance from the source node, that is 0 because it is starting from a itself, and the node. And in front of the priority queue we have this, right? So in the next step we go over to B, since there is a directed edge, right, from here to here, and no other edges exist. So we see that the distance to reach it is 5. So we add 5, B in the priority queue, and we have popped this starting one, that is 0, a has been popped out, and we update the table with the cost value equal to 5 for B, right? Then there are two paths from B to D and B to E. So we get to E and we update the cost from basically infinity is basically greater than the cost 5 plus 3, that is this value plus this value. So we update infinity with the value, the smallest or the minimum value, that is 8. And similarly here for D, 5 plus 20 equals 25. So we update these in the next step. So you can see 25 and 8 have been updated. Now elements in the priority queue remaining, because we pop this out. So elements in the priority queue are 8, E, 8, E, and 25, D. Right, 8, E, and 25, D. Now we see that we can, from E we can go to, and we pick the minimum. We are maintaining a minimum heap, so we pick the minimum element, minimum cost, that would basically be at the top of our priority queue because this is a minimum heap. So the minimum element would remain at the top, and the more distance we have, it would be at the bottom. So minimum distance at the top, that is 8 is at the top. So we pop this out and we basically traverse to its neighbors. We check this value is 25, right, and this is 8. So we check if 8 plus 7 is less than 25. That is true. So we update 8 plus 7, that is equal to 15 for D. And similarly for C, since it was infinity marked initially, 8 plus 10 is less than infinity, so we mark it as 18. Right, we updated it. Now priority queue 8, E has been popped out. Right. And then in the next one, basically this has been updated. Let me show you. Right, so D has been updated to 15. D value has updated to 15. C value has been updated to 18. That is 8 plus 10, right? And C to A we won't update because it was 0 initially, right? And finally, do not push A into the priority queue because we already have a lower cost for A, right? And next step is basically going to the end, that is from D to F. So this value is 15. So 15 plus 4 is equal to 19. So we reach F, and F cost is 19. So return distance, because the front of priority queue is the end node, and this is our destination. So this is the answer, that is the minimum or the smallest cost that we need to reach from A to F, that is from source to destination, using Dijkstra's. Right. So now the algorithm, let us go through it in depth. So initialization, when we initialize the graph class with n nodes and list of edges, we create an adjacency list representation for the direct weighted graph. We initialize an empty adjacency list, list, where each node's outgoing edges will be stored along with their cost. Then add edges. So when we call the add edge method from add an edge to the graph, we provide an edge in the form of list from to an edge cost. We extract from node to node and cost from the input edge, and we append a tuple or a pair to node and cost to adjacency list entry for from node, which represents directed edge from to node. This is the from node and this is the to node. So there's a directed edge from node to node with the specified cost, that is the edge weight, right? And the shortest path calculation, our main function, that is when we call shortest path, we need to return minimum cost path from node 1 to node 2 using the Dijkstra's algorithm. So we initialize array cost for node to keep track for the minimum cost to reach each node when starting from node 1, and a priority queue PQ to explore nodes in ascending order of their accumulated cost from node 1. Then we set cost for node of node 1 to 0 because we are starting from here. That is the source node. So the cost, or basically the distance to reach our source from our source itself, would be 0 because we are standing at that node itself, right? This is the source. And then we start by adding 0 comma node 1 to priority queue with initial cost 0 for node 1. While the priority queue is not empty, we continue exploring the nodes. For each iteration, we pop the node with the smallest accumulated cost, current cost from priority queue. If the current node is equal to node 2, we have found the shortest path, that is our destination, and we return the current cost. Then we iterate. If we have not, we iterate through the neighbors of current node stored in the adjacency list. So go over all the neighbors. For each of the neighbors, we calculate the new cost by adding the cost of the current edge, that is the edge, this edge, to the current cost that we have. So this is the edge weight. So that is the current edge. If the neighbor's new cost is less than its cost in the cost for node, we add new cost comma neighbor to priority queue, which means we will explore this neighbor with updated cost and additionally assign value of new cost to this one. So we update the cost for node with the minimum new cost that we have found out. If the priority queue is empty and we have not found node 2, it means there is no path from node 1 to node 2 that exists, and we return -1. So that's how the solution works, and this is the code part. So I've declared unordered map. Wait a second. Declared an unordered map. You can also do it using a vector pair of int to form the adjacency list, but I've used this, so let's go over my implementation. So unordered map would store our int and vector of pair of int comma int. So this will basically be storing our u. Int stores our node u from, that is the from node, and pair of int comma int would store our v comma weight, that is the node, the to node and the edge weight, right? So it is basically something like u to v and with the edge cost of weight. So that is what we assign here. So it takes the edges vector, and we traverse to each edge. We extract the u, v, and cost, that is h0, h1, and h2. And in the adjacency list of u, we push back the v comma cost, right? So that makes our directed graph. That is our adjacency list. So that is basically being stored in this data structure. Now add edge is the other function. So that takes the edge. So again, we perform the same thing, u, v, and cost we extract and push it back into the v cost. So that is the same thing we did. For the graph, we basically need to initialize it for the whole graph, right? So for each edge, we're going to be traversing. But in this, we have already been provided an edge, so we have to do it for this. Then we have int shortest path that takes node 1 and node 2. So that is the source node and the destination node. So we declare a priority queue of type int comma int, and it is a minimum heap. So basically, it would be storing our distance and the node value, right? So distance and node. So this is the minimum heap, and we have a basically the cost for node vector that we talked about here is the result vector, and it is basically of size n, and we are initializing it with int max. So we're initializing all the values with int max as I had shown you, right? So this was a, b, c, d, and for a we have 0. Other nodes we are initializing with infinity, right? This is the cost, and this is the node, right? And we initialize our starting node res of node 1 is equal to 0 and push it into the priority queue because this is the starting or the source node, 0 comma node 1, right? So 0 is the distance and node 1 is the starting node. So we check while priority queue is not empty, d is equal to pq dot top dot first and node is equal to pq dot top dot second. We extract the node and the distance values and pop it out. And for each vector in adjacency node, so basically for each neighbor that we have extracted from the adjacency list, we get the adjacency node and the distance that is going to be taken to reach from that node. So that is the distance between u and v. So we check if the distance plus d is less than the value stored in the result, right? So initially we have marked other nodes with infinity, right? So this condition would hold true, right? If distance plus d is less than that, we update the value of a result of adjacency node to distance plus d. So we are adding the minimum cost that is taken from this node to this node from u to v. We are updating it in the result vector, and we are pushing the d plus distance, that is the new distance, new cost, which is minimum, and the adjacency node, that is the neighbor, into the priority queue. And finally, when this whole while loop ends, that is the priority queue becomes empty, that is we have traversed the nodes. In case our result of node 2, that is our result of the destination, that is the destination node's result is still equal to int max, that was when it was initialized. That means we have not been able to reach node 2, right? So then we return -1, that is it is unreachable. Otherwise, if the value is not equal to int max, that means it has been updated. and that implies that we have been able to reach the destination, right? So we have been able to reach the destination from the source using any path, right? And the value is not int max, so we return that value. That is the shortest path to reach from source to destination using Dijkstra's algorithm. So that's it about the video, and thank you guys for watching.